Hi everyone, welcome to Modern Optimization Methods. In this part, we will introduce Chapter 2, the fundamentals of unconstrained optimization. In this chapter, let's briefly take a look at the contents in this lecture. So we will introduce what is a solution, the optimality conditions, and the two different ways to do the update, line search strategy and the trust region strategy. Finally, we will talk about the convergence of algorithms. Now, let's first take a look at the first part. What is a solution? In this part, we will take a look at what is global minimizer, local minimizer, as well as the strict local minimizer and isolated local minimizer. Now, before we take a look at those local minimizers, let's recall that in this chapter, we actually consider the unconstrained optimization problem, which is we try to minimize function f, and the variables are n-dimensional space x. This f, we assume that it is a smooth function. So what is a smooth function? We define it as twice continuously differentiable function. These functions are smooth functions. So in the following chapters, we will all consider the unconstrained optimization problem because we always start from the easy case. Then in the second part of this course, we will consider the constrained optimization, which is a more difficult one. Okay, let's first take a look at this figure. Now I plot a non-convex function here, where you can see that there are many valleys in this curve, and also there is a global minimizer here. However, a question is how you can identify the global minimizer. All right? So it is possible that you just stuck at one of the local minimizer. That means that you just stuck at this valley, right? So we need some tools to identify the global minimizer, which is actually a very difficult problem. However, how we can define mathematically the global minimizer? So this is what we will introduce in this part. Now, we give a mathematical definition for the global minimizer. So a point x star is a global minimizer if it satisfies this condition. So it actually means that the function value of f at x star is the smallest one. In other words, for any function value f at any point x, its function value will be greater than or equal to the function value at fx star. Okay, so in this case, x star will be the global minimizer. Right, so as I showed in this figure, you can see that this point should be the global minimizer. However, this is the mathematical definition. How to realize it or how to characterize it, we give the definition here. And for the local minimizer, as I mentioned before, that you may stuck at one of the valleys here. So the bottom of this valley is actually one of the local minimizer. So mathematically, the local minimizer x star is defined as that it has to satisfy this condition. The condition actually means that we can find a neighborhood of x star such that within this neighborhood, all the function values are greater than or equal to fx star. In this case, x star is called a local minimizer. All right? So whenever we referred to a local minimizer, we have a neighborhood, all right, corresponding to this x star. So notice that In this case, local minimizer, we also referred it to as a weak local minimizer, right? Now, let's take a look at strict local minimizer. So from the name, you can see that it has some extra conditions because it is more strict, right? So what is strict local minimizer? So it actually requires that there is a neighborhood of x star, that within this neighborhood, any point other than x star, all right, its function value should be strictly greater than fx star. In other words, fx star is the unique minimizer in this neighborhood, okay? So there is no other points whose function value is the same as fx star. Then x star will be the strict local minimizer. So I give two examples here to show the definition of strict local minimizer. The first one is a constant function, which means that at any point, function value of f is 2, okay? So for this case, actually any point is a weak local minimizer, all right? However, for this constant function, there is no point to be a strict local minimizer because all the function values, they are the same. You cannot find one function value which is strict smaller than others. So for the constant function, there is no strict local minimizer. And for the second example, as I showed here, is actually a quadratic function. I plotted here. And you can see that the strict local minimizer is achieved at x equals 2. Okay, so 2 is the strict local minimizer. And of course, this strict local minimizer is a weak local minimizer as well. So from here, the two examples, you can see that strict local minimizer must be a weak local minimizer as well. However, the converse is not true, as I showed here, right? Now, let's talk about the isolated local minimizer. From the notation, you can see the isolated means that it is actually alone. There's no others, right? So this is from the notation. So mathematically, what is a isolated local minimizer? Let's still give it a neighborhood, all right? So we can find, or there exists a neighborhood of this x star. And within this neighborhood, x star is the only local minimizer, all right? So the only local minimizer actually means that there is no other local minimizers within this area, all right? So this means that x star will be called an isolated local minimizer. Now, I still plot the quadratic function here, and you can see that x equals 2 is also an isolated local minimizer. So compared to the strict local minimizer, it seems that for this case, x equals 2 is both the isolated local minimizer and also the strict local minimizer. So a question is the isolated local minimizer must be the strict local minimizer, or vice versa? So we investigate the relationship of the two minimizers in the following. Right, so we can see that for isolated local minimizers, they must be strict local minimizers, all right? Because from the definition, the isolated local minimizer is the only minimizers within its neighborhood, all right? So there is no other minimizers. So it must be the strict local minimizers. However, if we take it in the other directions, then the strict local minimizers are not necessarily the isolated local minimizers. Why? Now, below, we give an example here. We got a one-dimensional function f is x power 4 cosine 1 over x plus 2 times x power 4, and we can easily check that at point 0, the function value is actually 0. Okay, and you can see from the figure that x equals 0 is the global minimizer. So now the question is whether this point is an isolated local minimizer. So we need to check in its neighborhood whether there are other local minimizers. Now let's take a look at the curve here. So you can see that as x tends to 0, there are actually many valleys for this function. And for each bottoms of the valley, there are actually a strict local minimizer. In other words, for any neighborhood of 0, you can always find a series of strict local minimizer. So this will violate the definition of isolated local minimizer. Therefore, in this case, x equals 0 is not an isolated local minimizer. Alright, so this is a counterexample showing that strict local minimizer may not be an isolated local minimizer. Now, before we end this part, let's introduce an important tool called Taylor's theorem. We will use this theorem frequently in our subsequent chapters. So we introduce it in the following. Actually, Taylor's theorem has been introduced for one-dimensional case in our undergraduate course. Now, we are introducing the multivariate cases. Okay, so notice here that function value f is mapping n-dimensional case Rn to a real scalar function. And we assume that f is continuously differentiable. Then for any vector p, we have the first expansion here. So this expansion actually means that if we calculate function value f at x plus p, we can do it like this. So the first term is f at point x, the function value. So this can be viewed as a constant term with respect to p. And the first term with respect to p is the gradient term. The gradient term is related to the point x plus tp. So x plus tp, here this t is some constant between 0 and 1. And we have gradient transpose p will be the first order expansion. So in other words, this term is actually the first order exact Taylor's series expansion. Alright? And if we do further assumptions that we assume that f is twice continuously differentiable, then we can have further second order Taylor series expansion like this. The gradient of f at x plus p, this point, can be expanded into 3 terms. So the first term is constant f at x. And the second term is with respect to the gradient of f at x. And the third term is related to the second order information. Notice that for the second order information, the Heysen matrix takes the value at x plus tp. Okay, so this t is some constant between 0 and 1. It exists such t, but we don't know which one. Okay, so this is the second order Taylor's exact expansion. And we will use the two equalities or two ways of expansion frequently in our subsequent chapters. Alright, now let's make a brief summary about this part. So in this part, we introduce what is a solution, including the global minimizer and local minimizer. So there are three types of local minimizer called weak one, strict one, and isolated one. Finally, we also introduce Taylor theorem, which is an important tool we will use in the proof of some theories. Okay, so we stop here for this lecture. See you next time.